In this presentation, I will talk about regression variable transformations. The outline of this presentation will be first to define and talk about marginal or partial effects of the effect of an independent variable on a dependent variable, then talk about regressions when we have quadratic terms, regressions with interaction terms, rescaling of variables, and rescaling of logged variables. So what is marginal or partial effect? It shows the change in the dependent variable y for a 1-unit change in the independent variable xj. So if we have a regression model of y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus u, the change in y over the change in x1, and that's the same as the derivative of dy over dx1, and this is basically beta 1. So in this simple case that we have here, the marginal effect is the coefficient. So the coefficient can be interpreted as the increase in y by beta 1 units for a 1 unit increase in x1. Now let's look at the more complex case. So here we would look at the model that has quadratic terms and interaction terms. But that is still a linear in parameters model because all of the parameters that enter here are still linear, only that the variables have quadratic terms here or they have interactions. So now the marginal effect is obtained by taking a derivative in respect to that variable. So if we're doing the change in y over the change in x1, well, x1 only appears here, so that would be the coefficient of beta 1. If we're looking at the change in y over the change in x2, well, that's the coefficient beta 2 plus, from the properties of the derivative, this is twice the coefficient of beta 3 times x2. So this is what this partial effect will be here with this with a quadratic term for x2. So notice what is happening here. This x2 term is not going away. So now we have a variable in our partial effect. So no longer just the coefficient, but we have a variable. Then if we do the change in y over the change in x3, we have the beta 4 coming from here, and then we have plus beta 5 times x4, and this is what is here. And then the change in y over the change in x4 would be beta 5 times x3. So in models that include quadratic terms, interaction terms, or other nonlinear terms, the partial effect here would be depending on the values of the independent variables, and it's no longer a constant. So again, we would see these more complex cases here later on. This is the formula for the partial effect with quadratic term, and that's the formula with an interaction term. So a partial effect can be estimated for each observation I by substituting xji. So let's say we have the change in y over change in x2. Well, this was the expression, and here we can actually plug in all of the x2 variables for each observation I. So here we have n observations, and we can estimate actually n partial effects, one for each observation. A partial effect can also be estimated for any value of the variable x2, not just for the values that are in the sample. So a partial effect at the mean, what we would do is we would substitute x2i with its mean, which is x2 bar, and that mean is obtained by just taking the average or the mean of x2i over all the i's. So it's the simple averages formula where we have 1 over n, the summation over all the i's of x to I. So the partial effect at the mean would be the same expression as above, except that I have replaced here each of the x2 i's, which is the average of x2. So it explains the effect of the independent variable on the dependent variable at the mean of the independent variable. So that's why we call it partial effect at the mean, because it's at the mean. Now, with the average partial effect, that averages the partial effect across all the I observations in the sample. So the average partial effect would be equal to 1 divided by n summation I equals from 1 to n of this expression here. So this one explains the average effect of the independent variable on the dependent variables. So now notice one thing though, is that because this is a constant and this is a constant, this this basically averages would transfer and come in right here. Well, if it comes in right here, we would have exactly this expression here. So in this case, both methods would result in the same partial effect. The partial effect at the mean and the average partial effect would be the same with this example. There are other examples where that may not be the case. Okay, so let's look at the regression that has a quadratic term that allows for a nonlinear effect of an independent variable on the dependent variable. So the model is still linear in parameters, but not in the variables. So here's how a regression with quadratic term looks like. So not only do we have x1 here, but now we have x1 squared. So notice that the variable is squared, but the parameter is still linear on it. So the marginal effect changing y over changing x1 would be, well, we are collecting beta 1 from here, and then we have twice beta 2 times x1. So this is the marginal effect. So this marginal effect is not constant and depends on the variable x1, on the value of the variable x1. If we want to find the minimum or the maximum point when this marginal effect changes from increasing to decreasing and vice versa, what we need to do is put this expression to 0. So if we put this equal to 0 and rearrange to find this one, x1, we would have minus beta 1 divided by beta twice beta 2, and that's the expression here. So at this value of x1 star, we would have that would be the minimum or the maximum point where this marginal effect changes from increasing to decreasing and vice versa. So here's an example where we have wage regressed on education, and this is the coefficient if we have a simple linear regression. So to plot this, we have education on the horizontal line, wage on the vertical line, and this is the fitted line that we have here. That's a simple regression. Now, let's introduce a quadratic term here, and this would be education squared. If we put education squared in here, we would have the coefficients for the education would change, and education squared would be an additional coefficient here. So if we plot now education against wage, what we're going to find is this is going to be the fitted line. Well, it's actually going to be a curve because now we have a nonlinear relationship right here. And so we have a line that is first decreasing and then it's increasing. And if we want to find the minimum marginal effect here, it's probably somewhere around here. To calculate it more rigorously, we would put x1 star equals minus beta 1 divided by twice beta 2. So I would pick up this coefficient here, right here, beta 1, and then divided by twice the beta 2 coefficient right here, and this would have 6.18. So at the education of about 6 years, we would have that would be the minimum effect, marginal effect at 0. So let's look at this marginal effect in more details. So here we have, we can calculate the marginal effect of education on wage. So let's go back. In the model of wage regressed on education, that was the simple regression model. The marginal effect of education on wage was the coefficient, and it was constant at 0.54. So basically, one additional year of education is associated with 0.54 dollars increase in wage. Now, when we have the model with quadratic term, the marginal effect of education on wage depends on education. So the marginal effect delta wage over delta of education was equal to beta 1 plus twice beta 2 times education. And if we substitute, these are the coefficients that we have. Now we can calculate, this is the formula for the marginal effect. We can calculate this at any value of the education. So let's pick a few values and calculate the marginal effect. So if I pick the value of 5 years of education, I just plug in 5 in this expression, and this is the marginal effect. I will also calculate it at 6.18 because that was the turning point we estimated on the previous slide. And as we see, the marginal effect is 0. Then I'll calculate at 10. I will calculate the marginal effect at 12.6. This is the mean education or the average education of the people in the sample. And here we have 0.63, and then at 15 years of education, 0.86. So the marginal effect at the mean again is 0.63, and that's the same as the average partial effect. So notice how now we're saying that at the mean or for the mean person or the average partial effect is 0.63. So for one additional unit, one additional year of education, salary would increase by $0.63. And that would be happening at the average education for a person. So at low levels of education, let's say 5 years, the marginal effect would be negative, 0.11, but at high levels of education, the marginal effect of education on wage is 0.86. So what we're seeing here is an increasing marginal effect. So higher education basically would have even stronger, more positive effect on wages. And so in the beginning, it's a uh, decreasing effect, but then we have positive and increasing effect. And so look at this. If we basically have 15 years of education, then we have basically the strongest and most positive effect on education. So we can basically say that there's increasing returns to education. So now let's consider another example. So here is where we have wage regressed on experience, and that is basically the effect of for one additional years of experience is associated with 3 cents more in wage. And here is where we put experience and experience square in the same regression. And this is what we see if we plot wage against experience. We see here a flat line. But here we have, okay, does this data look more, uh, is it more like a linear relationship, a nonlinear relationship? If we estimate it, this is what we see here with a quadratic term. So if we want to see where where is the highest point in this curve, it's about right here. I'm just looking at it visually. And if we want to estimate it more precisely, x1 star would be equal to minus the coefficient on the variable divided by twice the coefficient on the squared term of the variable, and that would be 24.3. So at 24.3 years of experience, we would have that we would see actually decreasing um, marginal effect, and until then, we would have increasing marginal effect. So let's calculate now this effect for several values of the experience. And so we're picking up the formula here for the marginal effect, substituting in the coefficients. And again, if we have its particular experience, we just substitute the value of experience here to calculate the marginal effect. So what happens here is that the average or the mean experience in 17 years, that's how much experience people have in the sample. So the marginal effect at the mean would be 9 cents, same as the average partial effect. So with a simple regression, we were estimating that there's a 3-cent effect. And now for the average person, we're saying that there is a 9-cent effect. So at low levels of experience, say at 10 years, the marginal effect is 0.18, but at high values of experience, the marginal effect is negative. And so what we can say here is that for people that don't have a lot of experience, each additional year of experience brings a lot in wages, 18 cents. But if you're at the end of your career with like 30 years of experience, that actually happens to have a negative effect on wage. So actually more years of experience even reduce the wage, and we have a negative effect. Okay, let's talk about interaction terms. So that's another form of nonlinearity. And here we, in addition to the independent variables of x1 and x2, we're actually putting an interaction of x1 times x2. If we take the marginal effect delta y divided by delta x1, we would have, here's the coefficient beta 1, and then we have plus beta 3 times x2. Notice that the marginal effect of x1 also depends on x2. So with quadratic terms, we had the marginal effect of a variable on the dependent variable depended on its own value of that independent variable. But right now we have depending on another independent variable. And so what we want to see here is, for example, if we see a positive coefficient here, positive coefficient here, we want to know with the interaction, is this coefficient going to be positive and significant, meaning the two effects are going to, individual effects are going to boost each other, or if this coefficient is negative, then basically these two effects, individual effects, are going to work against each other, or it may be insignificant, meaning no boosting or canceling out of these individual effects. So let's see empirically how that works out. Here we have a regression model of wage on education experience tenure and the interaction of education times experience. So the marginal effect of wage is the change in wage over the change in education. And so this would be the beta 1 from here plus beta 4 times experience. So now the marginal effect of education on wage would depend on the other variable experience. So if we want to just plot wage against education, there's no more a line because for each education we have several different levels of experience, and that's why we can no longer just give a line, but there are several points depending on what the experience is. So let's look at it in more details. Here is the original regression where wage is regressed on education, experience, and tenure. And we have that all of these independent variables have a positive and significant effect on wage. So now if we estimate a regression model with interaction term of education times experience, and we add this to the model, we actually see that this coefficient here is not significantly different from 0. If we add another term called, which is experience times tenure, that coefficient actually happens to be negative. So here, this means that even though experience and tenure have positive effect on wages, actually their interaction has a negative effect, meaning you will get a positive effect of experience on wage, positive effect of tenure on wage. But if you have both high experience and high tenure, then they kind of work out against each other to cancel each other out. So people that are at the end of their career have this canceling out of this effect is how I would interpret this negative coefficient. So let's look at several marginal effects. So here, the marginal effect would be delta wage over delta education. Notice that now that depends on experience on the other variable. And I pick up the coefficients from the previous slide. And so if I give different values for experience, I can calculate these marginal effects. So here I gave it 10 years of experience, 17, which is the average number of years of experience in the sample, and 30. And I just basically put these values in here and I calculated the marginal effects here. So at low levels of education, at low levels of experience, which is 10 years, the marginal effect of education on wage is 70 cents, but at high levels of experience, 30 years, the marginal effect of education on wage is 0.95. So here we see that there is like an increasing effect of experience of education on wage as experience is increasing. So shifting gears, let's talk about what happens when we rescale variables. So now this is optional. It doesn't have to happen, but it is typically nice to rescale a variable if its magnitude is too large or too small and the variable or the coefficient does not display well in a table. So again, it does not affect the results of the regression, but it's simply for readability and presentation sake. So for example, if we have a variable, it can be rescaled from dollars to thousands of dollars by dividing by 1,000. And if we want to rescale the variable from dollars to millions of dollars, we would just divide the variable by 1 million. So let's say we have the regression equation here, and we want to rescale the dependent variable. So if the dependent variable is multiplied by c, then what would happen is that all beta head coefficients are going to be multiplied by c. So here we multiply this variable by c, and in order to keep the equation as an equality, we would have to multiply all of the coefficients by c. So if the dependent variable is rescaled from thousands dollars into dollars, if we multiply that by 1,000, then what would happen is that all of the coefficients will be multiplied. Right here, the three coefficients will be multiplied by 1,000. So now let's see what would happen if we rescale an independent variable. So here xj is multiplied by c, then its coefficient, beta hat j, would be divided by c. So here we have the c times x1, and in order to make this work, we need to divide the coefficient beta 1 divided by c. These two would cancel out, so we have basically the same expression. So if an independent variable is rescaled, say from $1,000 into dollars by multiplying it by 1,000, then its coefficient will decrease by 1,000. So let's see how this works in practice. So we have data on CEO salary and the sales of the company and then the profits of the company. So here the CEO salary measured in $1,000. And so the mean is $865,000. So the CEO salary could also be measured in dollars if we multiply this number times 1,000. So that would be 865,864. In the same manner, sales is measured in millions of dollars. This is for the company. So it's this number here. So this one basically has more rounding than this number. And then if we want to convert it from $1,000,000 to $1,000, I put here K for thousand and D for dollars. We would basically just multiply it times 1,000, and that would be the value. So if we compare the mean for salary in $1,000 and the mean for salary in dollars, notice this is the comma and this is the dot because this is in $1,000. That's how it's measured. We basically have exactly the same number. Now, we may round this number so it doesn't look like that. We may round it to $865,000. And in this case, we would have loss of information. But that loss of information is only because we have rounding. The rescaling of the variables is just a matter of preference. There's no loss of information because these two numbers are basically the same, just rescaled of each other. And these two numbers are also just rescaled. So here we have the comma, here we have the decimal point. So either of these two ways is fine. Now, let's estimate the regressions with the rescaled variables and see what happens. So here we have as dependent variable salary in thousands of dollars or salary in dollars. So basically, this one here in $1,000 got multiplied by a thousand. So here we have sales in millions of dollars. So notice what happens when we go from here to here, where the dependent variable is multiplied by 1,000. What happens to this coefficient is this coefficient got $1,000, 1,000 times larger, and this one got rescaled by 1,000 times, and this one got rescaled by 1,000 times. So again, when we multiply the dependent variable by 1,000, all the coefficients get multiplied by 1,000. So notice here, if salary again is measured in thousands versus in dollars, if we multiply the dependent variable by 1,000, these coefficients get multiplied, all of them by $1,000. So on the other hand, now let's compare this regression with this regression. So here is just the independent variable here, which is in millions of dollars, and here is in thousands of dollars. So here the independent variable got multiplied by 1,000. So here the independent variable gets multiplied by 1,000, so its coefficient gets divided by 1,000. So same thing here. If the independent variable gets multiplied by 1,000, then the coefficient gets divided by 1,000. So now looking at and all of the other you see like how the other coefficients are still the same. That only affects the coefficient for the independent variable that gets multiplied by 1,000. The coefficient gets divided by 1,000. So now these are the effects of rescaling depending on whether we rescale the dependent variable from here to here and from here to here, or the independent variable from here to here and from here to here. So the rescaling of variables avoids the problem of very small coefficients. So for example, I would not use a regression output that has this number here. Because it's just very hard to read. So I would be indifferent between using all of these models, but we probably shouldn't be using a model that has such small coefficients. We should go ahead and rescale the variables. So now, what about log transformations or log variables? So sometimes variables are expressed in logs, such as log of y or log of x. And with logs, the coefficient interpretation is in percentages or elasticities. So variables that typically get logged are measured in dollars. Variables such as age and education that are measured in units should not be, in such as years, should not be logged. variables that are measured in percentage points, such as interest rates, because they're already a percentage, should not be logged. And logs can't be used if a variable has 0 or negative values. And taking logs often reduces problems with large values or outliers and helps with ensure the homoscedasticity and normality. So if we estimate regression models of, again, salary on sales, and we have all of the four combinations here, salary is not logged and here is logged, and here sales is not logged and here sales is logged. So if we actually look at all of these combinations, then we have the linear form, the log linear, the linear log, and the log log form. So as we interpret the coefficients and the results from this model, one thing to notice here is that the R squared is the highest for the log log form. So based on this criteria, we should be using the log log regression. Okay, so let's see what happens when we rescale a log dependent variable. Here, if y is multiplied by c, then all of the slope coefficients are the same, but the intercept is higher by log of c. So let's see why that's the case. Here we have, if this is the dependent variable, log of y, and here we multiply y times c, say 1,000, by the properties of the log. Log of two numbers multiplied together is the log of c plus the log of y. That's how logs operate. So basically, in order to make this equation work, we would put here plus log of c as the intercept, and that's what would change. So notice that none of the coefficients, the slope coefficients, which means the coefficients on the variables would change. So now if we rescale logged independent variable, we multiply xj by c, then all of the slope coefficients again would be the same, but the intercept would be lower by beta j times log c. So here if we have the model like that, but here is the logged variable, if we multiply this by log of c, by the properties of the logs, that would be equal to beta 1 times log of c plus beta 2 plus beta 1 times log of x1. So this term here, we would need to subtract it so that we have basically the same equation. So now again, this affected the intercept, but did not affect any of the coefficients in the regression. So same as above. So the conclusion here is that rescaling logged variables, whether the dependent or independent variables, will not change the slope coefficients. So here is how the summary statistics look for logged variables. So here we have salary, log of salary, where salary was measured in thousands of dollars. Here is the log of salary where the salary D was measured in dollars. And here again we have L log of sales, where sales is measured in millions of dollars, and log of sales that was measured in $1,000. So these are the mean values, and they all look like reasonable numbers here. So let's see how the regression results look like. So here we have log of salary in thousands and log of salary that was measured in dollars. And that's repeated here. And we have the log of sales in millions and the log of sales that was measured in thousands. So one thing to notice here is that as we go from a regression to regression, nothing happens to these coefficients. They're identically the same, and this coefficient is identically the same. What changes is basically the constant. Um, and this is because of the properties of the logarithm. But again, we don't really care about constants as much or the intercept as much. So the conclusion here is that rescaling a dependent or independent variable that is logged would not change the slope coefficients, only the intercept. So if If, say, the regression output does not have very good coefficients for the log variables, there's not much that can be done to change that. So here are the review questions. Explain marginal or partial effects. Describe how the partial effect at the mean versus the average partial effect is calculated. Does adding a quadratic term change the marginal effect? And how does adding an interaction term change the marginal effect? And if the dependent or independent variables get rescaled, how do the coefficient change? And what if the variables are in logs?